All right. Welcome back to part two. We're now going to go over some of the sampling methods that would allow us to essentially generate samples for complicated distributions. The first sampling method is called the inversion sampling. This is one of the easiest method that we know. So, in order for us to understand inversion sampling, you need to understand what a function inverse is first. Well, with a function, we know how a function works. Essentially, we plug some x value, right? And then from the x value, it essentially tells us some kind of y value, right? So that's the direction is like this way. That's the direction. Now, inversion the inverse of a function, which is denoted with this inverse symbol, basically you just do it backwards, where you solve the equation in in terms of x. So you're looking for x. So you're actually plugging y in, you're getting x out. So the direction looks like this. You plug y in, right? And then you get some kind of x value out. That's essentially a function inverse. Okay, so hopefully that picture is clear. The difference between this way versus this way, right? That's an inverse. So the other concept that we learned previously is called the CDF of a probability distribution. Essentially, a CDF is a function such that when you plug this value in, x, it this function returns the area all the way up to that point. So it's returning the entire area all the way here. So if you had your x being x hat, which was right here, then it will essentially try to find the area all the way to here, right? All the way to here. So that would have been the area. So the function essentially gives you the area. So if we were to use this function on a really simple distribution for Bernoulli, for example. So here's a Bernoulli where the probability of 0 is 0.3 and the probability of 1 is 0.7, right? So they add up to 1. So in this case, if we try to look at the the CDF of this, right? So at every single point, in the beginning is 0 because there's nothing that happened. So it's adding up the area. So the area is 0, 0, 0, 0, 0, all until you reach the point 0. Once you reach the point 0, you're going to add this portion, which is 0.3. So it goes here and kind of jumps up. It jumps up. And then after that, it kind of, from this point, it's going to add 0, right? So it's going to keep adding 0, 0, 0, 0. At this point, then it jumps up again because it adds 0.7, right? So this area is 0.7. So it jumps up. And therefore, the CDF of a Bernoulli distribution looks something like this. You notice how at 0, it jumps up by 0.3, and then it keeps adding 0 until it reaches 1. So it jumps up by 0.7, and then it stays at 1. The CDF has a really interesting characteristic because the area of probability total has to equal to 1, right? No matter what, the total area. Therefore, as you add up the area throughout the CDF, it will invariably start with 0 area and reaches 1 area. So the CDF is always between the range of 0 and 1. That's the point. So what is interesting is we can now combine the idea of CDF with the inverse function. So here's the CDF function, right? And now let's take a look at the inverse of the CDF. Notice that the value is always between 0 and 1. Therefore, if you generate random samples between 0 and 1, such as 0. 0.1, 0.2, 0.6, right? What is the result of plugging these values into the inverse? Right, let's first look at 0. 0.1. If we plug 0. 0.1 in here, and we plug this value into the inverse CDF, so the CDF inverse, the result is going to be 0. So with 0.2, right? It will also, so it would generate, so this is 0, this is 0. But if we pick 0.6, notice the result would have been 1. So when we're trying to generate Bernoulli distribution, it's essentially you're generating either 0 or 1, right? So you notice how by generating random uniform distribution, you're able to then generate 0, 0, 1. Now, ideally, you want to generate 0 at a certain probability, which is 0.3, and you want to generate 1 at 0.7. Notice that if you're uniformly generating samples between 0 and 1, right, the probability that you're going to land in this area is 0.3. And the probability you're going to land in this area is 0.7. This implies that the probability of you generating a 1, right, a 1 is 0.7. And the probability you're going to generate a 0 is 0.3. So the probability of generating 0 and probability of generating 1, right? So if you were to generate a lot of samples, then 30% is going to essentially be zeros, and 70% is going to be ones, generating the exact same probability distribution we want. Okay. Now, from this distribution, we can, that was a simple Bernoulli distribution. But over here, we can extend this idea to a continuous distribution, such as if we use an exponential distribution. So over here is the exponential distribution, and over here is the CDF of the exponential distribution. So here's the CDF. Now, from the CDF, we can essentially find the CDF inverse by solving for x, right? So if we just solve for x right here, this implies that if we just generate a uniform distribution between 0 and 1 and plug it in here, we would essentially generate the samples for x. And these samples would turn out to be an exponential distribution. Okay? So let's practice idea. Like, in order for you to really understand, you have to like actually see it happening. So let's write the code that uses inversion sampling to generate an exponential distribution with mean of 2. First, generate sample of a uniform. So that's what you do. Once you generate uniform distribution values as v, you plug it in here. And then these are your exponential distribution samples, as we just saw, right? This is the same result. The distribution of x should be exponential. And so what you want to do is plot the histogram and visually see that it is indeed exponential. And then you want to essentially draw it. So over here, you want to show it's exponential, and then you want to draw it. So you want to draw the histogram as well as the equation. Okay, you can pause the video, do this. The solution is actually here. You can see that this is p of x, and over here is the histogram.